right, so how does it work? Well, it's not real hard. We take analog electrical waveforms and we convert them into digital optical pulses. Okay. All we're doing, right, binary code, we're signaling with binary code. We're taking a light switch and we're turning it off and on. Right? Light there, that means a 1. Light off, that means a 0. Binary code, simple. Okay. How fast we can modulate that determines how fast we can send signal or bandwidth is. Right? So in the simplest form, we take an electrical waveform, turn it into optical light pulses, receive them at the other end, and turn it back into an electrical waveform. Make sense? We understand that? Yes?
Is there also amplitude measurement too, or is it only binary?
Yes and no. Okay, there are certain applications where you are looking at amplitude within the fiber in terms of light pulses, but purely for the sake of our discussion today, we're going to talk about digital signaling. Okay, so that's how it works from the electrical and optical perspective. How does it work from the media perspective, the actual physical media of optical fiber? What optical fiber is made of, and in its very basic component, is glass. Okay? And we've got the core of the fiber and then cladding, both of which are glass. The core and the cladding have a different chemical makeup or density, right? And what that allows is it allows us to shoot light into it, and by what's called total internal reflection, I can keep the light within the core of the fiber depending on the angle at which it's traveling in there. Okay? I'm not going to get super technical on this, but think of it this way. The analogy I like to use for this is a lake. Okay? If I'm standing on a hillside and I look down at a lake, if I'm standing at a particular angle, I'll see a reflection of the sky, right? So that's called refraction, and what's happening is the light's getting bent by the differences between the density of the air and the density of the water. Okay? If I move down the hillside and get closer to the lake on a different angle, I'll reach a point where I no longer see the reflection of the sky, but I see through the water into the bottom of the lake. Okay? At that point, I've exceeded the critical angle, and now I'm not seeing the refracted light. Does that make sense? That's the simplest way I've come up with to explain how this works. It's all about the angle at which the light travels into the fiber, right? Because it's two different densities or grades of glass, the core and the cladding. Light will strike the cladding and bounce within the fiber if it's within the critical angle. Okay, so here was one of your questions. What's the difference? Single mode, multi-mode. Okay. Obviously, the prefixes are pretty straightforward. Single, one, multi, more than one. When we talk about mode, what we're talking about is a path for light to travel through the fiber. And I've got another slide that shows this better. Okay. But from the very basic portion of the fiber, the cladded fiber, the core and the cladding, just the glass, single mode fiber has a core diameter of 9 microns. Now remember how big I said the human hair was in diameter? 127. So the light carrying portion of a single mode fiber is 9 microns. Okay. Then it has the cladding layer, which takes it out to 125 microns in diameter. There's two prominent styles of multi-mode right now. The older being 62.5 micron core and the newer being 50 micron core. Okay. So we'll talk more about the differences between those, but just understand that there's two different types of multi-mode. And the core diameter is much larger. So here's the first question to win yourself a piece of swag. Which has higher bandwidth, single mode or multi-mode?
Single.
Why? Based on core diameter, why?
Because.
Okay, so and the analogy I like to use for this one is the garden hose versus the fire hose.
Smaller diameter, less light to light up the entire surface.
So, but if I use the garden hose fire hose analogy, what more water comes out of which?
Fire hose.
Okay, so it would stand to reason that if I have a larger core, I would have more light, right? Okay.
But it is scattered, so when you focus it, you get a
Winner. Do you want, and scattered was the right word, because we'll explain what that means in more detail. Water bottle or stadium blanket?
water bottle.
All right.
Hit me. Thanks.
Okay. All right. I'll get to that. I'll get to the scattered piece.
Okay.
As far as the light spectrum, the electromagnetic spectrum, the visible light that we can see exists between about 425 nanometer wavelength and about 775 nanometer wavelength. So it's a very small portion of the electromagnetic spectrum that we can actually see as light and colors. The area that we use for signaling in optical fiber is in the infrared range, between about 850 nanometer and 1625, or a little bit higher in some cases. So it's invisible, you can't see it. This is a key thing to remember, because it can harm you.